Raspberry Pi and circuit simulation. Falstad simulator, buck switch mode power supply. We can start this process by looking at the falstad.com website. This is the default screen we should see. We're going to go to the full screen version. We're not particularly interested in this circuit. We're going to look at a switch mode power supply, and we have in circuits here, power converters, boost, and there's the one we want to look at today. That's the buck converter. So there's a simplified buck converter. We'll just grab the circuit and move it up towards the top and give us more room to see the oscilloscope display, which is down here. The default mode is to have the two channels side by side, but we're going to look at it top and bottom stacked. So what is it that we're looking at? Well, the top trace is in fact this oscillator, or the clock, and the bottom one over here is the output. It takes a little while for the circuit to stabilize, and we can speed it up by running it faster. Notice that the variation in the output stops, and we can slow it down if we want to see the detail a bit better. Now, how do we go about zooming in on the time scale? Well, we start by either right mouse clicking on the top trace or looking at the little gear here, and we can change the horizontal scale to, well, let's say 100 microseconds. And we're going to change the name, the label here. We're going to call it clock. Okay, there it is. There's the clock which is running the circuit. And you'll notice that the output is running at about 3.4 volts. Now that output voltage is a function of the duty cycle. The duty cycle now is 72%. You can see it right here. If we vary that, we will vary the output voltage. So let's take a look at that. We can vary it right here on the right hand side, the duty cycle. If we decrease the duty cycle, the output voltage begins to fall. And you can see it dropping. And if we obviously increase the duty cycle, the output voltage begins to rise. Now it takes a while for the circuit to stabilize as it goes through quite a few calculations. So again, we can speed up the simulation to get the result a little faster. And there it is, stabilizing. And there we have the output. So we're just going to crank it down to someplace in the middle. Now if we want to see the amount of ripple on the output, the way we do that is either right mouse click or click on the gear here and change the vertical scale from auto to max scale. And we're going to call this output voltage. There it is, and again, simulation takes a while to stabilize, so we can run it up a little faster. It's doing its wonderful calculations, and eventually it achieves stability. And there we have it. We have the ripple. Now you might wonder, how much is that ripple? Notice that in this particular case, the RMS output is, it says 2.239 volts RMS. Well, we can take a look at that by showing the peak value and then the negative peak value. And so there we have it. It's a maximum 2.248 and a minimum is 2.231. So a relatively small amount of ripple. Very nice. So circuit's working very, very well. Now what we'd really like to see is what's happening in all the circuit components, to see where the currents are flowing and when they flow. But to do that, we really have to zoom in a little bit further. To do that, we go to Options, Other Options, and we can change the time step, which is by default 5 microseconds, and that's the time step used internally in the program, to something like 1 microsecond. Apply it, OK, and notice that the output has expanded. We've zoomed in. And so if we run it a little bit faster to see what we have, we notice that we see one complete cycle on the oscilloscope trace. Well, that's really zoomed in. So let's reduce it from 20 microseconds per division to, let's say, 50 microseconds per division. And now we'll actually should see 2 complete cycles of the sine wave. And there we go, 2 complete cycles of the clock. Now, to find the current in the transistor over here, the MOSFET switch, we just right mouse click on it, View in New Scope, and we will stack it, and we'll change its properties. We're already looking at the current. We're going to show the scale. We don't need to show the duty cycle, and we're going to call that MOSFET Current. And there it is. So I notice that when the switch is high, when the clock is high, that current is flowing through the MOSFET. And when the switch is off, the clock is low, no current is flowing into the circuit. And notice that this corresponds to the current flowing in the MOSFET corresponds to the negative half cycle of the ripple. Now let's take a look at the current flowing through the diode. We're going to view in a new scope, stack it. We're going to label it Diode Current. Okay. And notice that when the current stops flowing in the MOSFET, it starts flowing in the diode, and vice versa. So let's take a look at what's happening in the inductor. View a new scope, stack it, and we'll call it Inductor Current. And notice that the inductor current is the sum of the 2 currents, the one from the diode and the one from the MOSFET. Notice also that the inductor current is unidirectional. It never reverses. Now, it's a little bit hard to see at the moment because what we've actually looked at is the max scale. So we're looking at the maximum and minimum values of the ripple. So to change that again, we'll look at Properties, and we'll just go to Auto. And notice now we can see here's 0 amps, and the current is always positive, always positive. We're going to add to that the capacitor current. So let's just view a new scope, stack it, and we'll label it Capacitor Current. Okay. Now notice something interesting here. Here is the 0 line, 0 amps, and the current in the capacitor is AC. If we wanted some details on what's actually happening, we could show the peak values, the positive, the negative one, and the RMS value. So let's just do that. And notice that the maximum value is about 681 microamps. The minimum is minus 682 microamps. And the RMS value is, there we are. The RMS value is 394 microamps. And if we show the average current is virtually zero. Let's take a moment and look what happens when the MOSFET turns on. Current flows through the MOSFET, through the inductor, and into the load. No current is flowing in the diode, and current in the capacitor is going in and out. When the MOSFET turns off, current continues to flow in the inductor and the diode and load. The current in the capacitor is going in and out. When current flows into the capacitor, it is positive. When current flows out of the capacitor, it is negative. Here are a few of the notes to explain how this simplified circuit works.